Welcome to PLANETA 3D. Thank you and congratulations for choosing the introductory session on 3D printing. It's 2020, an awaited year which was predicted as a revolutionary year. Indeed, it has happened so. In this pandemic situation of COVID-19, a technology which has emerged as a boon for mankind is 3D printing. In Italy, this technology came into rescue for hospitals when valves to reanimate medical devices were not available and traditional manufacturing ways were shut. Worldwide, it's seen that an informal network of hobbyists and manufacturing firms are using 3D printers to make tens and thousands of T-pipes, face masks, shields, ventilators, and lots of other medical equipments and products which were needed but unavailable in market. 3D printing is definitely the future's technology and an essential part of Industry 4.0. Industry 4.0 is the fourth industrial revolution. What it is and why you should care. So, the fourth industrial revolution is the fourth time human beings started using advanced technology to solve the problems. Humans first started using mechanism, water power, and steam power. Then, secondly came mass production, assembly line, and electricity. Third was computer and automation. And fourth is 3D printing and cyber physical system. People often wonder that are 3D printers too difficult to handle and operate? Well, in its time of origin, this technology did need only highly trained professionals to operate because 3D printers were initially designed specifically for engineers, architects, surveyors, or other technical professions. Earlier, 3D printing technology seemed to be some science fiction that was difficult to understand and even more difficult to perform. But exploring its vast utility in every big and small field, towards 21st century, experts have successfully made 3D printing a lot more simple, user-friendly, and easy to access. 3D printers are now available for common consumers at ease and at affordable price too. In this introductory course, I am sharing some basic information about this revolutionary technology which will definitely make you capable enough to get started with 3D printing. Thanks again for joining us. Go ahead and enjoy the session. Many times, people misinterpret 3D printing as lenticular printing, but in reality, it's a different, unique, and revolutionary concept. 3D printing is in fact a manufacturing technology. It's a new way to manufacture products, be it a single piece or mass production. But then why it's called 3D printing? Let's elaborate. We all are aware that 3D means three-dimensional, that is height, length and breadth. Almost all physical objects around us are 3D, like trees, buildings, vehicles, human, birds and everything. Now what's printing? Printing is a process for reproducing text and images using a desired color, ink or any material using a machine. The printers which are used in office and homes are 2D printers, two-dimensional, that is length and width. Now, combining both the concepts of 3D and printing, this new term 3D printing came into existence. First a CAD file is designed and then the print command is given to the machine. So this machine is called printer that prints in 3 dimensions and the process is called 3D printing. Magic! This process is also known as additive manufacturing process. Earlier, products were manufactured either by subtractive manufacturing process or formative manufacturing process. Formative manufacturing typically forms material into desired shape through heat and pressure. The raw material used can be melted down and extruded under pressure into mold, which is known as injection molding or die casting, or pressed and pulled into the desired shape, which is called stamping, vacuum forming, and forging. The design of formative tooling is also complex, with the need for mold features like spurs or runners to assist in the formation of parts. Parts that are produced through formative manufacturing also have design constraints like draft angles and uniform wall thickness to aid in the forming process. Subtractive manufacturing typically forms material into desired shape via punching or CNC. In this process, from a block of material, the unwanted material is removed to obtain the shape of the desired object. Subtractive manufacturing is almost a wasteful production process, as large amount of material that is often removed to produce the final part, and so lot of waste is left. Biggest hurdle is that complex geometrical shapes are not at all possible. All these hurdles in production makes additive manufacturing technology very appealing to the industry because it has potential to be precise, cost-effective and time-saving in terms of production. In additive manufacturing, layer by layer is added. Each layer is cooled and combines with the lower layer to form the material into desired shape. Instead of carving out shape from a large chunk of material, which is quite wasteful, production of 3D objects using a 3D printer could mean using just required material to make a product. This mode of production is the method of creating an object from a digital design. So, parts can be produced in almost any geometry, which is one of the core strengths of additive manufacturing. 3D printing does not rely on expensive tooling with essentially low startup cost, and the biggest advantage includes rapid verification, development of prototypes, and even production of functional parts for end use. And that's not all. The most interesting part is that additive manufacturing can also be used to make mold, die, and punch, which are used in formative and subtractive manufacturing. Wow! I just love 3D printing technology. Applications of 3D printing. 3D printing will disrupt every field it touches. In recent years, 3D printing technology has developed significantly and can now perform crucial roles in many mainstream applications. Let's understand the process of 3D printing. Suppose we want to create this model. First, a CAD file is created with a 3D modeling program or scanner. Later, as it is sent to the printer, the software slices the design into thousands of horizontal layers. These layers of material are then printed successively until the physical object is created. 3D designing. The first step towards 3D printing is by creating a CAD model, that is, Computer Assisted Design Model. Now, these drafting programs were previously developed strictly for engineers and architects. But as 3D printers are becoming more useful to consumers in various fields, software used for 3D designing have become easily accessible and user-friendly. In fact, software for this recent technology has quickly adapted to the need of its eminent market, which is more likely any person who is interested in doing these things the DIY way. To patch a 3D image directly with a 3D printer, you would need to use a software that can save the image in the STL format. Softwares used for 3D designing are Paint 3D, SketchUp, Art of Illusion, 3D Crafter, BRLCAD, FreeCAD, LeoCAD, OpenSCAD, MashLab, Tinkercad, AutoCAD, 123 Design, Blender, Rhinoceros, ZBrush, SolidWorks. The designing software that you choose should depend on your design purpose. A beginner will likely opt for Paint 3D, Tinkercad, 123 Design or Google SketchUp. An artist is more likely to be in tune with Blender, Rhino or ZBrush, while a product designer will likely utilize AutoCAD or SolidWorks. Of course, there are no such rules on what software to be used because ultimately it depends upon an individual's compatibility. Let's have a demonstration of 3D modeling with Paint 3D, which is published by Microsoft.
There's a lot you can do with the primitive 3D shapes in Paint 3D, like this cube. Use the top rotation tool to adjust the angle of your object. The rotation tool on the right can be used to tip your model back and forth. Use the orbit tool on the bottom to spin your model around, and use the last tool on the left to move your model back and forth in space. Plus, grab any edge of your selection and pull it in or out to adjust the depth of your shape. It's easy to use the adjustment tools in Paint 3D to turn basic shapes into something totally new.
Let's also have a demonstration of 3D modeling with Tinkercad. 3D scanning. 3D scanner is another important tool in 3D printing. For more understanding, let's compare it with a flatbed scanner, which is commonly used to scan documents and images. Scanned files can be used as a digital reference and preserved. Also, it can be used to make multiple copies from it. Scanned file is also very easy to send via internet or storage devices to others. In the same way, 3D scanner solves the purpose. It stores 3D properties of the scanned object that can be used when needed. How does a 3D scanner works? Switch on and hold it. Move the scanner around the object. Save the digital replica file. Do some corrections or editing if needed and give print command. The 3D printer does the rest. Let's see a demo of a beginner's level 3D scanner made by XYZ. For professionals like architects, interior designers, car modelers, statue makers, artists, etc., one of the best 3D scanner. are different high-range 3D scanners for terrestrial scanning, for surveyors, and big turnkey projects. STL and slicing. In order to 3D print a product, a CAD model must be converted into a format that a 3D printer is able to interpret. This begins by converting the CAD model into a stereolithography, that is STL file, also referred to as Standard Triangle Language File. OBJ or 3DP file format are also compatible but are less frequently used. STL uses triangles, that is polygons, to describe the surface of an object, essentially simplifying the often complex CAD model. Most CAD programs are capable of exporting a model as an STL file. Once an STL file has been generated, the file is then imported into a slicer program, which slices the design into horizontal layers that will be used to build up the object. The slicer program takes the STL file forward and converts it into a G-code. G-code is a numerical control programming language used in CAM to control automated machines like CNC machines and 3D printers. The slicer program also allows the operator to define the 3D printer build parameters by specifying support location, layer height, and part orientation. The slicer programs are often proprietary to each brand of 3D printer, although there are some universal slicer programs like Cura, Netfab, Simplify 3D, Slicer, etc. If you are a designer, you only need to provide the 3D printer operator with an STL file. The operator will then set the desired parameters for the print and produce the G-code file themselves. Types of 3D printing processes. In 2015, to standardize and define different methods of 3D printing, an ISO ASTM 52900 standard was formed. 7 types of 3D printing processes were categorized, which are as follows: material extrusion, vat polymerization, powder bed fusion, material jetting, binder jetting, direct energy deposition, sheet lamination. Let's discuss these technologies associated with the processes and also description of the processes. Material extrusion process. Here, material is selectively extruded through the nozzle or an orifice. Fused filament fabrication (FFF) technology, commonly also known as fused filament deposition (FDM), operates under this process. FDM is a term trademarked by Stratasys. This technology is more commonly spread and also consumer friendly. The material comes in form of a string of solid thermoplastic material known as filament. Filament is pushed through heated nozzle and gets melted. In melted form, it's extruded on the built bed in a G-code programmed manner. Filament gets cooled, solidifies, and forms a solid shape. Once a layer is complete, the build platform moves down and the process repeats, building up the part layer by layer. Supports are required to the structures which has overhangs less than 45 degrees and bridges longer than 20 mm. FFF technology is used in both low-cost desktop 3D printers as well as high-end industrial machines. Low-cost desktop FFF printers are technically similar to their high-end industrial counterparts, but their capabilities differ. Industrial printers use a tightly controlled environment and are able to automatically adjust printer settings to suit the print material. The controlled environment in particular means that the parts are printed in an enclosed space with temperature and humidity both regulated. This reduces the rate at which parts cool down, limiting the likelihood of wrapping or distortion. Most industrial machines also use dual extrusion, allowing support structures to be printed in a dissolvable material. Because of the controlled build environment, industrial machines generally produce parts of a greater accuracy with a high level of repeatability. The build volume of industrial machines are also larger, allowing bigger parts or a greater number of parts to be produced in a single build. For this reason, industrial machines are being utilized for low to medium raised production runs. Desktop FFF machines offer a low-cost and rapid method of 3D printing. The accuracy of desktop machine is generally adequate for most applications. As hardware, materials, and software continuously improve, the gap between industrial and desktop FFF is decreasing. Apart from the increased build chamber offered by the industrial machines, modern desktop printers are highly accurate machines offering dual head extrusion for dissolvable support materials or multi-material prints, bringing parts of industrial quality to the desktop. In addition, desktop 3D printers allow more control over the print parameters compared to industrial machines, making them ideal for prototyping. Nowadays, even DIY kits are being introduced, which are available at very cheap rates, but their performance can't be compared to desktop 3D printers. DIY 3D printers has an open body structure, so extra precautions are required to operate, like exposure to dust, harmful effects on use of certain materials, and also sometimes not at all safe for children. Filaments comes in different materials like ABS, PLA, nylon, PETG, TPU, PEI. ABS and PLA are most commonly used materials. Preferably, PLANETA 3D promotes PLA because it's eco-friendly and not harmful as ABS. Special kinds of PLA filaments are also developed, which are made from fruits and vegetable extracts, specially for educational purpose, keeping in mind safety of children. Previously, PLA filaments didn't have strength, But now, new PLA Plus material have equal strength to ABS. In FFF technology, CFF, that is Composite Filament Fabrication, is an addition from Markforged, where composite materials are used to give more strength to the product. Metal FFF also is an addition in desktop market. Metal X and DM Studio prints in metal impregnated plastic filaments. In addition, even Ultimaker has introduced a composite printer. Voxel 8DK printers deposit conductive metal filled paste and thermoplastic polymer and allows the production of parts with integrated electronics. VAT polymerization process. Here, liquid photopolymer in VAT is selectively cured by light activated polymerization. Stereolithography (SLA) and direct light processing (DLP) technologies operates under this process. SLA is famous for being the original 3D printing technology. The term stereolithography itself was coined by Charles W. Hull, who patented the technology in 1986 and founded the company 3D Systems to commercialize it. In this technology, there is a mirror, each at x-axis and y-axis. Mirrors are known as galvos. Design is broken down in layer by layer into series of points and lines that are passed to galvos as a set of coordinates. Most SLA machines used a solid-state laser to cure parts. DLP uses a digital light projector screen to flash a single image of each layer all at once, or multiple flashes for larger parts. Since the projector is a digital screen, the image of each layer is composed of square pixels, resulting in a layer formed from small rectangular bricks called voxels. DLP technology in workflow is similar to SLA, but is more faster and accurate since it uses the screen and full layer is exposed all at once. LED screen or UV light source is used for projecting the light onto the resin that is directed to the build surface by a digital micromirror device DMD. This DMD generates light pattern where light is projected on the build surface. Standard DMDs have a resolution of 1024 by 780, while standard SLA printers uses a laser with 130 to 150 micron spot size. This can vary depending on the size of the machine. VAT polymerization machines are able to produce parts in two different orientations, bottom up or top down. SLA and DLP printers come in both configurations with the design depending on the manufacturer. Both configurations have their respective advantages and disadvantages. VAT polymerization 3D printers are also available in grades of industrial and desktop 3D printers and DIY kits. As with FFF, The main difference between different grade wet polymerization 3D printer is the build environment. Industrial machines use a regulated environment, higher DMD resolution, and are therefore able to produce more accurate parts and utilize a large range of engineering materials. Desktop printers can produce parts to an accuracy of 100 to 250 microns, while industrial machines are capable of 10 to 30 microns. Higher accuracies generally also lead to a better surface finish. DIY printers, again, are very cheap and solves the purpose of just learning or getting introduced to the technology. Materials used in vat polymerization process are standard resin, transparent resin, castable resin, tough resin, non-castable resin, also known as high temperature resin, dental resin, and flexible resin. Vat polymerization parts are most suitable for visual application and prototyping, where a smooth surface finish and high accuracy is desirable. Some of the most common applications of vat polymerization are injection mold-like prototypes, jewelry, investment casting, dental application, hearing aids. In vat polymerization process, new technology, continuous direct light processing (CDLP), also known as continuous liquid interface production or CLIP, is invented. CDLP produces parts exactly the same way as DLP. However, it relies on the continuous motion of the build plate in the Z direction, upwards. This allows the faster build times as the printer is not required to stop and separate the part from the build plate after each layer is produced. The resin is cured by using combination of LED and oxygen. Powder bed fusion process (PBF), in which thermal energy selectively fuses regions of a powder bed. Selective laser sintering (SLS), direct metal laser sintering (DMLS), selective laser melting (SLM), electron beam melting (EBM), multi-jet fusion (MJF) are technologies that operates under this process. Most PBF technologies employ mechanism for applying and smoothing powder as a part is constructed, resulting in the final product being encased in powder. The main variation in PBF technologies come from the differing energy sources, for example, lasers or electron beams, and the powders used in the process, plastic or metals. Selective laser sintering (SLS) creates paths layer by layer. SLS produces solid plastic parts using a laser to sinter thin layers of powdered material one layer at a time. The process begins by spreading an initial layer of powder over the build platform. The cross section of the part is scanned and sintered by the laser, solidifying it. The build platform then drops down one layer thickness and a new layer of powder is applied. The process repeats until a solid part is produced. The result of this process is a component completely encased in unsintered powder. The part is removed from the powder, cleaned, and then it is ready for use or further post-processing. SLS is best suited for producing strong functional parts with complex geometries. This, coupled with the isotropic nature and high level of accuracy, sees the technology often adopted for the production of end-use parts. The other big advantage of the SLS process is that the parts do not require any support material. This means support does not need to be removed after printing and also results in a consistent overall surface finish, as there is no negative effect from support being in contact with a build surface. selective laser melting (SLM) and direct metal laser sintering (DMLS). Both produce parts in the similar method to SLS. The main difference is that SLM and DMLS are used in the production of metal parts. SLM achieves a full melt of the powder, while DMLS heats the powder to near melting temperatures until they chemically fuse together. DMLS only works with alloys like nickel alloys, Ti64, etc., while SLM can use single component metal such as aluminium. Unlike SLS, SLM and DMLS require support structures to compensate for the high residual stresses generated during the build process. This helps to limit the likelihood of wrapping and distortion. DMLS is the most well-established metal additive manufacturing process with the largest installed base. Electron beam melting (EBM). EBM uses a high energy beam rather than a laser to induce fusion between the particles of a metal powder. A focused electron beam scans across a thin layer of powder, causing localized melting and solidification over a specific cross-sectional area. EBM produces less residual stresses in parts, resulting in less distortion and less need for anchors and support structures. Moreover, EBM uses less energy and can produce layers at a faster rate than SLM and DMLS. But the minimum feature size, powder particle size, layer thickness, and surface finish are typically of lower quality. EBM also requires the parts to be produced in a vacuum, and the process can only be used within conductive materials. Multi-jet fusion (MJF). MJF is a new technology invented by HP. MJF 3D printers works in a similar method to other PBF technologies with one extra step added to the process, a detailing agent. MJF is combination of the SLS and material jetting technologies. A cartridge with inkjet nozzles similar to the nozzles used in desktop 2D printers passes over the print area, depositing fusing agent on a thin layer of plastic powder. At the same time, a detailing agent that inhibits sintering is printed near the edge of the part. A high-power IR energy source then passes over the build platform and sinters the area where the fusing agent was dispensed, while leaving the rest of the powder untouched. The process repeats until all parts are complete. In March 2020, Prisma Health named HP as its manufacturing partner for manufacturing ventilators using 3D printing technology. Also, this machine, compared to traditional SLS printers, is said to be 25% faster due to a large reduction in cooling time after printing and the way energy is applied.
Introducing the HP Jet Fusion 3D printing solution, made up of a printer, build unit, and processing station with fast cooling. With a more efficient 3D printing workflow, now you can deliver functional parts up to 10 times faster at the lowest cost. The process begins with HP's easy-to-use software, which allows you to prepare the build to be printed, including error checking and automatic packing of your 3D models within the build chamber, before sending the job to print. For materials loading, the build unit is inserted into the HP Jet Fusion 3D processing station. Pre-packed HP materials cartridges are installed and quantity and mixing options selected. The materials transferred to the build unit in a clean and automated process before it is slotted into the printer so production can start. Pre-print and in-printer checks enable predictable quality output. HP's multi-jet fusion technology delivers extreme dimensional accuracy and optimal mechanical properties faster. And thanks to HP's unique multi-agent printing process, you have voxel by voxel control over each part. The material is contained within the HP Jet Fusion 3D build unit at all times, meaning the printer can easily switch between a range of different materials. The material is raised from inside the build unit and spread evenly across the build platform, where the fusing process occurs. The build platform is then lowered layer by precise mechanisms, which help ensure a high degree of dimensional accuracy. At any point during the printing process, you can monitor job status in the command center. The build unit is removed from the printer and taken to the processing station, and the second build unit installed, so you don't have to stop production. The HP Jet Fusion 3D processing station allows for cooling, unpacking, and mixing via a semi-automatic process, which helps reduce labor costs. Fast cooling speeds up the post-print process, and the powder is contained entirely within the processing unit, ensuring cleaner unpacking and materials reuse and mixing. During unpacking, a laminar airflow ensures all unused material is stored, ready to be recycled for the next job. Any remaining unused material can be recovered manually to provide the highest possible reusability rates. Once cooled and unpacked, the parts are ready for processing in a bead blast cabinet before any final finishes are applied. The unused powder is recycled and mixed with fresh material, and once the build unit is filled, the processing station is ready for the next job. The HP Jet Fusion 3D printing solution offers the possibility to print using different materials. The HP Jet Fusion 3D external tank provides the option to extract recycled material from the processing station, so it can be replaced with a different material. You can rely on HP's world-class services and support to maximize uptime and productivity. HP Jet Fusion 3D printing. Start producing more functional parts within the same day, up to 10 times faster, and at the lowest cost.
Materials used in PBF are nylon, alumide, PEEK, TPU, aluminium, titanium, stainless steel, nickel alloys, cobalt chrome, carbon fiber filled nylon. Material jetting process, in which droplets of material are selectively deposited and cured on a build plate. Material jetting MJ, drop on demand DOD, and nanoparticle jetting NPJ technologies operates under this process. Material jetting MJ works much like a standard inkjet printer. However, instead of printing a single layer of ink, many layers are built upon one another to create a solid part. The print head jets hundreds of tiny droplets of photopolymer and then solidifies them through a UV light. After a layer has been deposited and cured, the build platform drops down one layer thickness, and the process is repeated to build up a 3D part. Material jetting process requires support, and this is often printed simultaneously during the build from a dissolvable material that is easily removed during post-processing. Drop on demand DOD printers have two print jets, one to deposit the build materials, typically a wax-like material, and another for dissolvable support material. Similar to other AM techniques, DOD printers follow a set path and jet material in a single moving point to generate a cross-sectional area of a component layer by layer, which is unlike material jetting that deposit material in a line. These machines also employ a fly cutter that skims the build area after each layer to ensure a perfectly flat surface before printing the next layer. DOD technology is typically used to produce wax-like patterns for lost wax casting, investment casting, and mold making applications. Nanoparticle jetting NPJ uses a liquid which contains metal nanoparticles or support nanoparticles loaded into the printer as a cartridge and jetted onto the build tray in extremely thin layers of droplets. High temperatures inside the build envelope causes the liquid to evaporate, leaving behind metal parts. Material jetting process is ideal for realistic prototypes, providing excellent details, high accuracy, and smooth surface finish. Material jetting allows a designer to print in multiple colors and multiple materials in a single print. The main drawbacks of material jetting technology are the high cost and the brittle mechanical properties of the UV activated photopolymers. Materials used in material jetting are rigid, transparent, rubber-like, ABS-like, stainless steel, ceramics, wax, multi-material and multicolor printing. Binder jetting process, in which a liquid bonding agent selectively binds regions of a powder bed. Binder jetting prints in a similar fashion to SLS, with the requirement of an initial layer of powder on the build platform. Unlike SLS, which uses a laser to sinter powder, binder jetting moves a print head over the powder surface, depositing binder droplets, typically 80 microns in diameter, that binds the powder particles together to produce each layer of the part. Once a layer has been printed, the powder bed is lowered and a new layer of powder is spread over the recently printed layer. This process is repeated until a solid part is generated. The part is then left in the powder to cure and gain strength. After this, the part is removed from the powder bed and the unbound powder is removed via compressed air. After printing, the parts are in a green state and require additional post-processing before they are ready to use. Often, an infiltrant is added to improve the mechanical properties of the parts. Ceramic-based binder jetting is ideally suited for applications that showcase aesthetics and forms, architectural models, packaging, ergonomic verifications, etc. It is not suitable though for functional prototypes, as the parts are very brittle. Ceramic-based binder jetting can also be used to create molds for sand casting. Metal binder jetting parts can also be used as functional components and are more cost-effective than SLM or DMLS metal parts, but have poorer mechanical properties. Materials used in binder jetting are silica sand, PMMA particle material, gypsum, stainless steel, ceramics, cobalt chrome, tungsten carbide. Direct energy deposition DED process, in which focused thermal energy is used to fuse materials by melting as they are deposited. It is predominantly used with metal powders or wire and is often referred to as metal deposition. Laser engineered net shape LENS, and electron beam additive manufacture EBAM are the two technologies using BED process. Laser Engineered Net Shape LENS utilizes a deposition head which consists of a laser head, powder dispensing nozzles, and inert gas tubing to melt powder as it is ejected from the powder dispensing nozzles to build a solid part layer by layer. The laser creates a melt pool on the build area and powder is sprayed into the pool, where it is melted and then solidified. The substrate is typically a flat metal plate or an existing part that material is added on. Electron beam additive manufacture EBAM is used to create metal parts using metal powder or wire welded together using an electron beam as the heat source. Producing parts in a similar fashion to LENS, electron beams are more efficient than lasers and operates under a vacuum, with the technology originally being designed for use in space. DED technologies are used exclusively in metal additive manufacturing. The nature of the process means they are ideally suited for repairing or adding material to the existing components such as turbine blades. The reliance on dense support structure make DED not ideally suited for producing parts from scratch. Materials used in TED are titanium, stainless steel, aluminium, copper, tool steel, copper nickel, 4340 steel. Sheet lamination process, in which sheets of materials are bonded to form a part. Ultrasonic additive manufacturing UAM, laminated object manufacturing LOM are technologies that operates under this process. The sheet lamination 3D printing technique is mainly used to produce colored object in a high detailed resolution. As a build material, thin layered material like aluminium foil or paper-based filaments are cut into appropriately shaped layers, often by lasers or a very sharp blade. Layers are coated with adhesive and successively glued together layer by layer, similar to other 3D printing technologies. The precision of the result depends mostly on the thickness of layered materials used. Objects that are printed with this technique may be additionally modified by machining or drilling after the printing process is completed. Sheet lamination is a low temperature process and is used for making models for display. The process is quite useful for making visual models speedily at low cost. The process is, however, not suitable for making structural or functional models. That is why, even for prototyping, sheet lamination process has limited use. The process is generally used for making dummy models for demonstration purpose only. So, this process is not frequently used worldwide as compared to other processes. With this, let me summarize the session. In this session, you got introduced to Industry 4.0, what is 3D printing, 3D designing, 3D scanning, and above all, 7 different 3D printing processes and 18 different technologies based on each individual process. PLANETA 3D has an expertise at 3D printing lab setups in schools, colleges, and educational institutes, which is also promoted by Government of India through Atal Innovation Mission. PLANETA 3D has an expertise and provides industrial solutions like rapid prototyping, 3D scanning, 3D designing, and industrial 3D printing lab setup at manufacturing units. 3D printing pen. Indeed, 3D printing is the future technology. It's observed that people do have a talent of designing but lack to visualize the 3D properties of the object. It's best to create a practical 3D sketch of product with 3D pen. It provides in-hand experience. It's a fun learning for 7 years and above. They can have the 3D object making experience with 3D pen art making. A 3D pen is controlled neither by a computer nor requires any software or any coding. It's guided instead by your own hands as you create a model entirely from your imagination. A 3D pen is like a handheld 3D printer, but it's pretty much like drawing with a pencil or a pen. A 3D pen works in one of the two ways depending on whether it's a hot end or a cold end. A hot end pen uses plastic filament which is inserted into the pen where it's heated and extruded. As the molten filament leaves the pen, it's rapidly cooled, giving desired object on the surface. A cold pen takes advantage of a chemical process to convert a liquid to a solid. This is possible because the ink is in fact a photosensitive resin. Once it leaves the end of the pen, it solidifies using UV light. A 3D pen is a serious tool for architects and professionals for product development team to have a 3D sketchwork. On the other hand, it's an effective tool when used for crafts, drawing, and creative arts. A 3D pen is a must for practical learning experience when it comes to the classroom for students.
Attention boys and girls, men and women. Get the power of unlimited creativity by 3D pen technology from PLANETA 3D.
Американская фирма Transceptor Technology приступила к производству компьютеров «Персональный спутник».
Before I conclude, PLANETA 3D has specially designed Beginner's Lesson Pack. The Beginner's Lesson Pack is the perfect package to introduce young learners to 3D printing. There are 7 lessons, including 7 modeling tutorials, all based on Tinkercad with easy to follow step-by-step instructions. This is great for ages 10 and above. Enhance your skill set and boost your ability through innovative and independent 3D printing technology. So, what are you waiting for? Click on the link provided below and enroll for the package now. Keep 3D printing, and thanks again for visiting PLANETA 3D.